Let me give you two jobs. Job 1, what is 12 times 12? There is exactly one right answer and I can check it instantly. Job 2, write me a warm 2-line reply telling a customer their order is late. Now, what is the right answer to that? There isn't one. There are 1,000 good ones and 1,000 bad ones, and no test you can run that prints a green check. This is the whole problem with teaching an AI to be helpful, kind, clear, or tasteful. Taste has no answer key. So how do you train a behavior you cannot even grade? You already saw the seed of the answer back in Season 1. You do not tell the model what is right. You show it, over and over, that this reply is better than that one. Today, we open up exactly how that is done in 2026, and one surprisingly simple idea that quietly took over the field. Let's quickly rebuild the machine we left in Season 1. It has a name you'll hear everywhere, RLHF, reinforcement learning from human feedback, and everything today is about taking it apart. The trick was that judging is far easier than writing. You cannot handwrite the perfect reply to every prompt on Earth, but a person can glance at 2 replies and say which is better in seconds. So you collect a mountain of those judgments. This answer beats that one millions of times. Then came the clever and rather heavy machinery. First, you trained a whole second neural network called the reward model, whose only job was to imitate those human preferences and hand out a score. Then you put the main model, the policy, into a reinforcement learning loop. The classic one is called PPO. It writes an answer, the reward model scores it, you nudge the policy toward higher scores, and a leash stops it from drifting too far from where it started and just gaming the score. That leash has a name too, the KL penalty, basically a measure of how far the model has wandered from its original self. It worked. It gave us the first genuinely useful assistance, but look at how many moving parts that is. A reward model to train and maintain, a finicky reinforcement learning loop, a leash to tune, 3 machines bolted together on a conveyor belt. Now here is the idea that changed everything, and it is genuinely elegant. Researchers proved something almost cheeky with the math. They showed that the score the reward model was learning and the language model you were trying to improve are 2 sides of the very same coin. There is an exact equation linking them. So your language model is, in disguise, already its own reward model. The score lives implicitly in the model's own probabilities. And if that is true, you do not need to build the separate reward model at all. You do not need the reinforcement learning loop at all. You can take those same human preferences, this answer beats that one, and rearrange the math so it tunes the main model on them directly with one simple training step, the same kind you would use to sort cats from dogs. Watch what that does to our conveyor. The reward model station, unbolt it, gone. The reinforcement learning loop, unbolt it, gone. The whole assembly line collapses down to one move. Take a preferred answer and a rejected one, and push the model to make the preferred one more likely and the rejected one less likely. This is called direct preference optimization, DPO, and it is so much simpler and steadier that it swept through the field. But be careful, because this is exactly where people get it wrong. DPO did not throw the leash away. If you only ever shouted make the good answer likelier and the bad answer unlikelier, the model would happily distort itself into something strange to obey you. So DPO keeps a frozen copy of the original model, the reference model, as an anchor, and every nudge is measured relative to that anchor. Make the chosen answer more likely than the reference would, the rejected answer less likely than the reference would, but stay tethered. There is even a single knob, a dial usually written as beta, for how hard you are allowed to pull away from that anchor. It is the same KL leash from before, just turned into a number you set. Loosen it and the model changes fast but can wander into nonsense. Tighten it and it stays safe but barely learns. Same balance as the old loop, chase the preference but do not drift too far from yourself. DPO did not delete that wisdom. It just folded it into one clean training step instead of a sprawling loop. So the headline you may have heard, that DPO replaced reinforcement learning, is only half true. It replaced the heavy reward model plus loop for teaching taste. It kept the soul of the leash. Once one clean idea like that lands, a whole family grows around it, and it is worth knowing the shape of the family without getting lost in it. You'll hear these names, so let me give you a one-line map. Some relatives change what kind of feedback you need. One called KTO learns from plain thumbs up and thumbs down on single answers. No need to line up two replies side by side, which is often all the data you can actually collect in the real world. Others try to be even leaner. One called ORPO folds the preference step directly into the very first training stage, so there is no separate frozen anchor and no second pass at all, one stage instead of two. Another, SIMPO, drops the anchor too and instead simply rewards the model for preferring shorter, cleaner answers over rambling ones. The honest truth is that there is no clear champion. Which one wins depends on your data and your task, and the differences are often small. So the practical picture today is simple. DPO and its close cousins are the workhorse for teaching taste. Not a single magic algorithm, a small toolbox, all built on the same core move you just watched. Raise the good, lower the bad, anchored to where you began. Now step back because everything so far has been about taste, the things you cannot grade. Helpful, warm, well-judged. But remember job one from the very start, 12 times 12. For a huge class of problems, there absolutely is an answer key. A math problem has a known result. A piece of code either passes its tests or it does not. And when you can check correctness automatically, something wonderful happens. You do not need human taste, and you do not even need a learned reward model. Correctness itself is the reward. People call this verifiable reward, and tuning a model this way has a name: reinforcement fine-tuning. A separate cousin of these methods exploits it. Instead of one answer, the model writes a whole group of attempts at the same problem. You check each one. The ones that got it right get pushed up. The ones that got it wrong get pushed down. And the cleverest part, you judge each attempt against the average of the group. So the model only learns from doing better than its own typical try. That group against its own average trick is the heart of the method you'll hear called GRPO. Notice it throughout yet another machine. Even the separate critic that older reinforcement learning used to estimate a baseline is gone. The group is the baseline. No human raters, no preference pairs, just a checker. This is the engine behind the modern reasoning models, and one warning before you file the name away. GRPO is already half a generation behind. It had stability problems, so the field has moved on to refined successors. You'll hear names like GSPO and DAPO, and that is genuinely where the frontier of this is in 2026. We unpack that whole algorithm and its successors in its very own episode. So today, just hold the contrast. When there is an answer key, you reward correctness directly. When there isn't, you reward preference. Here is a question that breaks a lot of intuitions. If a giant, expensive model has learned to reason beautifully, do you have to put a small model through that whole grueling training to make it reason too? Surprisingly, often no. You can just have the big model show its work, write out its full step-by-step reasoning on thousands of problems, and then train the small model to plainly imitate those worked-out chains. Copy the route, not just the destination. In fact, researchers found that for a small model, copying a strong model's reasoning traces this way beat running the heavy reinforcement learning on the small model directly. The student learns faster by watching an expert than by struggling alone. And this points at something bigger that now powers the whole field: synthetic data, where AI generates the very examples used to train the next AI. It is everywhere now because human-written data is finite and expensive. But it carries a real and famous danger, and you have to get this exactly right. The danger is called model collapse, and the headline version of it is genuinely scary. Train a model on its own output and its children get worse, and their children worse still, until the whole thing curdles into bland mush. The rare, surprising, colorful parts of language, the tails, thin out and vanish. Each generation forgets a little more of the real world. It is true, and it has been demonstrated. But here is the part that almost everyone leaves out, and it changes the whole story. That collapse happens when each generation replaces the real data with synthetic data, throwing the originals away and drinking only from the previous model's well. When researchers instead accumulate, keep all the original human data and add the synthetic on top and curate it, filter out the junk, the collapse largely goes away. So the lesson is not synthetic data is poison. The lesson is, do not feed the model only its own reflection. Keep it anchored to reality and be picky. And to be clear about the scare stories, no frontier model has actually collapsed. This is a known failure mode that careful labs design around, not a doom that is unfolding right now. So pull it all together. Teaching taste, where there is no answer key, means showing the model that this beats that 1,000,000 times, and DPO made that almost shockingly direct. Teaching correctness, where there is an answer key, means rewarding what you can check. And feeding the next generation means copying good reasoning and curating synthetic data without ever cutting the cord to the real world. No separate magic, no single algorithm that replaced all the others. Real systems chain these stages together. First, imitate good answers, that's the fine-tuning step. Then teach taste with DPO, then reward correctness with verifiable reinforcement learning. Imitate, prefer, verify. That is how a raw next-word predictor becomes something that feels like it actually has judgment.